Welcome to this presentation by EGS India. As a part of the Dimensional Management series of presentations, we are pleased to provide you with a new presentation titled Answers to Quality Challenges Using Sigmund. We hope you enjoy this presentation. The agenda of this presentation starts with an introduction to EGS India, followed by enumeration of the challenges in quality as faced by the manufacturing industries, step-by-step procedures in using Sigmund to overcome these challenges in quality forms the next part of the presentation, followed by integration of Sigmund in product development process and overview of the same, summarized with the benefits towards the end of the introduction of Sigmund as a part of the product design and development process. EGS India was started in 1993, primarily with the emphasis on design engineering consulting. Dimensional management expertise is a part of the core development team at EGS India. We are a Sigmund authorized solution provider in India. Sigmund suite of tolerance, stack-up, and assembly build analysis solutions is provided by the developers Vara Tech Incorporate USA. Product design and development specialists with application in varied segments. EGS is known for its capabilities in understanding and developing products based on fit, form, and function. We have a core team which comprises of people with practicing GD&T professionals with proven capability in solving problems faced by the manufacturing industries. Typical problems faced by the industries start with assembly issues. Components not fitting together, interfering with each other, forms a big part of the assembly issues that delay the overall production or influence the productivity of the organization. Tighter tolerances are expensive to maintain is another challenge, where costs are going up exponentially as the tolerances are tightened for higher precision. In other words, the cost of precision being very high, the profitability of the company suffers as a result of that. Vibration issues as a result of the center of mass of rotating assembly not lining up with the instantaneous axis of rotation, leading to performance degradation, vibrations, noise, premature failure. These are a part of the quality issues. Inconsistent vibrations across multiple assemblies is another issue. Inconsistent product performance, let us say it is a valve or a pump or any other equipment which is failing to meet the requirements, maybe with regard to durability, maybe with regard to efficiency, maybe with regard to the overall performance, not because of a poor design, but because of the tolerance variations. Another issue confronted by the design and development team all the time. I do not know why this product failed while the rest of them passed. Higher rejections coming as a result of tighter tolerances, or higher rejections because the process has gone out of control, or higher rejections because the components are not coming into assembly all the time. Return to the design department and they tighten the tolerances. How to eliminate these high rejections is always a constant source of worry for the organization, because the profitability of a company lies in its scrapyard. Field failures and warranty issues affect not only the product performance, not only the product's life cycle, but also the company's image. It could be a result of the dimensional variations that are not captured as a part of the product design and development process. A question to ponder is, the same drawings were used for the products performing without issues and failed products. Same suppliers manufactured the parts. Same assembly line was used. Same operators manufactured and assembled the products. Then why do some products fail in assembly or performance while others do not? The answer lies in understanding the concept of variations as provided by the tolerances on the drawings. These could be dimensional, as I stated on the drawings. It could be a material variation, it could be an assembly variation, it could be operator bias, forces either during assembly or during function, temperature. These are some sources of variation that a person needs to understand or a team needs to understand to try and bring them under control for a consistent quality in the products to meet the challenges that have been said ahead. Every design team is confronted with two types of issues. One is, how do my part tolerances affect my assembly tolerance or my assembly measurable specifications in terms of quality? Second is, I have an assembly requirement in terms of quality, measurable specifications. What should be the individual tolerances at the part level to achieve the same for the least cost? The first one is called as the tolerance analysis. The second one is called as tolerance synthesis. The Sigmund terminology for that is roll up for tolerance analysis and roll down for tolerance synthesis. Let's take an example of a sprinkler assembly as shown here. This would help us to understand the Sigmund process and differentiate it from the conventional methods in order for the companies to benefit. The components that go into the sprinkler assembly start with the body, then the washer is inserted, the swing arm, which is yellow in color, is placed on top of it, while the jet gets assembled on the inclined shaft on the body. The cap gets put on top of the swing arm, and that's how the components are assembled. A cut section view, as shown here, helps us understand the assembly process and how the components interact with each other in this assembly. So we have the cap in blue color, the swing arm in the yellow color, the body in the gray color, and the jet in a brown color, with the washer going between the swing arm and the body. The first objective would be the clearance between the swing arm and the cap, as shown in this picture. A closer look of the same would reveal the different dimensions that are taking part in this vector loop of clearance. Inside Sigmund, the parts are created in the Sigmund Stanks approach, which is a non-CAD interface. CAD interfaces are available with ProEngineer, SolidWorks, and Solid Edge, while non-CAD interface does not require a CAD license. The drawings can be taken as the source of information to put it together inside the Sigmund interface. The working environment of Sigmund provides a project window comprising of the assembly and the build objective windows. The assembly hierarchy with the parts and their feature dimensions with their tolerances find their place in the assembly window under the projects, while the design for quality objectives, which are measurable specifications, come under the build objectives. The dimensions are populated according to the assembly hierarchy inside the assembly window as shown here. The dimensions and their tolerances could be either plus or minus, or could be any combination of the 14 characteristic symbols used in the geometric dimensioning and tolerancing approach based on the feature control frame. These dimensions could be enabled, or the data could be obtained from a live process data, and then subsequently the build objectives are put together. Here, the gap or the clearance or the flush, as shown here as an example, is used as the build objective. This is where we define our DFQ objective. Now, for forming the vector loop in the tolerance stack-up analysis, a node tree approach is provided by the Sigmund interface. This is a patented methodology provided by Varatech, unique in its own way because it is easy for us to do simple small sub-assemblies first before we start building up the main assembly. It's a building block approach. Now here, all we have to do is drag and drop each and every one of the contributors that are coming in from the different part dimensions in the assembly as shown here. Component dimensions, which are coming from the same component, are grouped together as shown on the right side. So subnodes comprise of sub-assemblies, main assembly could comprise of subnodes, and contributors directly coming from parts getting assembled at the top level. So the top-down approach can be used here because of the node tree approach. Different kinds of analysis are provided for in the Sigmund interface. The worst case analysis, the square root of sum of squares or the RSS method, the modified RSS method which deals with shifted means of the processes from 1.4 to 1.7, and then the process-centric RSS where the CP/CPK of the processes for the individual features to maintain their tolerances are given in terms of the CC values. And subsequently you have the Monte Carlo simulation which goes through in a random methodology dictated by the Monte Carlo methodology. Now you have the roll-up calculation coming in, wherein for the individual part dimensions and their tolerances, what is it going to be at the assembly level? The values are shown over there as 3 plus or minus 0.525. That would have been the clearance between the swing arm and the cap as a result of the tolerances that have been provided at the part level. The roll-up and the roll-down calculations and the different methodologies or the tolerance stack-up analysis methods are provided in the toolbar, which can be easily picked up, and the person can do an analysis at the touch of a button. Now, once we know what is that we can get, now we can introduce what we really want. In this particular example, it could be 3 plus or minus 0.25. Then in that case, that becomes the limits that specifies within which the desirable tolerances need to lie in. As a result of doing this, you get the assembly yield in terms of ppm and the CP/CPK of the assembly to specify where we are with regard to what we need. The contributors from the different dimensions are given in the sensitivity report, expecting the manufacturing and inspection to follow them closely with regard to those contributors which are significant as compared to the insignificant ones. In other words, the critical to quality indicators come in directly from the sensitivity report. Objective function number 2, clearance variation between the swing arm and the jet in a direction which is not in line with the assembly direction, leading to multi-dimensional tolerance stack-up as shown here. The different contributions are coming from the washer thickness, which is in the vertical direction, having its direction cosine component coming in, the float and the swing arm to the body, again contributing in the trigonometric direction, trigonometric contributions, and then the swing arm profile, the jet length, and the body end profile. These are the contributors that go in together to form what is called as the vector loop as shown in this picture. So multiple build objectives can be built. There are no limitations to the number of build objectives a particular product may take on. So the trigonometric factors are provided as shown over here. The third build objective becomes the clearance between the cap and the body. The contributors for the same are shown in this picture. Each one of them is lined up inside the Sigmund interface, dragging and dropping again, and performing the worst case calculations as required. And the last one is nothing but the clearance in the build objective 4 between the body shaft and the swing arm. Since this is directly related to the size dimensions between the two components, diameters, it is specified right there and the worst case analysis is performed. Till now we have done the roll-up calculation. Now we need to know the roll-down calculation as compared to the roll-up, wherein we specify the desired values for the tolerances in the assembly and what should be the individual part tolerance for achieving the same. It comes in a very simple step. As you can see, it's a touch of a button and you get on the right side of every one of those squares the roll-down values. The top node has the desired levels. The bottom ones have the contributory levels that would have led to the desired sequences. And then you have the washer thickness which is locked because it's a barred out item which is not under our control in terms of the specification for the tolerances of the thickness of the part. And then you have the body shaft length specified here as the tolerance gets tightened from 150 microns plus or minus to 100 microns plus or minus. We need to remember this because there's something else coming up interestingly subsequently down the line. The PPM clearance, PPM for the clearance between the swing arm and the cap is provided here. The contributors before and after and the level to which their contributions have changed are provided here in the roll up as well as in the roll down for this particular study. Then you have the build objective 2, the clearance between the swing arm and the jet, the PPM levels for the same, the contributors for the same. This exercise is repeated for each and every one of the build objectives. Now here you go, clearance between the cap and the body. Now here you see the body shaft length recommended values of 187.5 microns plus or minus as compared to 100 plus or minus 100 microns in the first build objective. These run contrary to each other. So if the same dimension were to be forming a part of multiple build objectives, how do we handle that? We'll come to that in a minute. Here we have the PPM again shown as the clearance between the cap and the body, which shows the specs, number of components out of spec is insignificant so that we can tighten the tolerance. Sensitivity again comes in before and after the roll up and the roll down. And then we have the fourth build objective, again the roll down calculations over there, the PPM for the same, the sensitivity for the same and the changeover after the roll down. And then you have the Monte Carlo simulation here showing for 10,000 pieces how the histogram would look. Essentially what we have done is we have tried to arrive at the tolerances for the individual build objectives. However, there are certain contributors which are common between different build objectives. In one case it could be a minimization of a value, in another one it could be a maximization of a value. That's where the tolerance optimization across build objectives comes of use. Sigmund has a very powerful optimizer which goes across multiple vector loops without any limitation based on the weighing factors which is given at the bottom of each one of those dimensions. The weighing factors is nothing but the cost of precision. You take that, you go through the optimization and you get the global optimization report. This tells you what has changed, what has not changed, in which part it has changed, in which dimension it has changed, and what was the method of analysis that was adopted to arrive at those values. Many reports can be generated using Sigmund: the statistical reports, the sensitivity report, the optimization report, and you could get the min-max from the optimization report, or you could get only the tolerances which were increased or the tolerances which were decreased separately in each report so that you know exactly where the changes have been made. And then you get the global summary report, the cost savings report, the statistical process control report that needs to go to the manufacturing and the inspection for them to adhere to, and then the tolerance analysis reports. Versatility of Sigmund lies in its report generation, as you can see here. Now, if we were to implement this as a part of the dimensional management process in an organization for product design and development, how would it stand? The current practices are given on the left, where you start with the product specification, provide a detailed engineering design, prototype development follows that, assembly fitment issues start coming, you go back to the design department, tighten the tolerance, rework and delay, ECNs and tool changes, money runs out, cost is running out, and the time is also running out, and it's a never-ending cycle till the product and the processes are perfected. In the right-hand side approach, which is nothing but the Sigmund approach, you have what is called as the product specification, going back to the design for quality objectives, then the tolerance analysis study, the least cost tolerancing, the first time right assembly, launching and monitoring the CTQ. The cycle never repeats itself. So the best-in-class dimensional management practices are incorporated in the Sigmund process, as you can see here. What are really the benefits of the tolerance analysis method as proposed by Sigmund? Understand part variations and their effect on the assembly quality upfront. Optimize the tolerances for meeting the quality norms. Strike a balance between the cost of precision and the cost of poor quality. Investigate and find solutions to quality issues based on contributors and their sensitivities. The CTQs in these cases are objectively selected and not subjective. This ensures consistent quality by monitoring the process trends and maximizing the yield. Typically, some of the organizations try and do a spreadsheet approach for doing this kind of calculations, especially for simple linear plus or minus tolerancing. If it is GD&T, Sigmund stacks can be used. If it is plus or minus, Sigmund stacks can be used. If it's a combination of GD&T and plus or minus, Sigmund stacks can be used. The worst case analysis finds itself in both the stacks approach as well as the spreadsheet approach. The RSS, again the same way in stacks and spreadsheet. Incorporating the process capability, incorporating and understanding the process deviations and their effects, the Monte Carlo simulation, the tolerance synthesis approach to arriving at tolerances, cost of precision analysis, large assembly stack-up analysis, tolerance optimization, PPM estimation, and report generation in terms of SPC, cost savings, optimization, sensitivity, and statistical reporting are something that Sigmund stacks overwhelms as compared to the spreadsheet approach. What have we learned from this presentation? How to perform a tolerance stack-up analysis without a CAD license, how to specify tolerances at the part level to meet the assembly build quality objectives, which tolerances are critical to quality, how to maximize the tolerances for least cost, how to ensure consistent quality. Did you like this video? If you say yes, please give us a like. And also we request you to provide your comments so that we can improve our presentations. If you are interested in further information on Sigmund or our services, please contact us at info@egs.co.in or visit our websites at www.egs.co.in or egsindia.com. Thank you.